Thank you, everyone. Thank you, David, and organizers for this opportunity. So in the next 15 minutes, I will sort of try to briefly summarize about our attempts to understand the accretion that is happening in the core of the protoplanetary disk systems. And towards the end, I will also mention about a future instrument we are currently building. All right, so this is a slide which really needs no introduction to the group here, but nevertheless, this is a cross-section of a protoplanetary disk, and you can see over the lower right corner, the beautiful images from ALMA. This is all thanks to the over the innovations in the sub-millimeter field over the last few decades. We have now exquisite images of the structures in the outer part of the protoplanetary disk. But today, the community here is more interested in the core part of the disk, which is unfortunately not yet resolvable, though the optical interferometers and near-infrared interferometers are almost there. That core part where the accretion is happening is really the heart of the system. Now, that completely determines the energy budget of the system, like the temperature of the disk, the chemistry of the disk, and so on and so forth. So it's really important to understand that inner part of the disk, where the accretion is happening. And for many reasons, like the accretion is, one of the problems in the exoplanet field is, for example, how do you form planets in this disk over the short time scale we have there. And the chemistry of the disk, everything, as I said, is completely determined by the accretion and the outflow, the energy budget of the system. And we, of course, unfortunately cannot spatially resolve these systems yet. But that has never stopped us astronomers from studying something. Traditionally, whenever we can't resolve something, we fall back to spectroscopy and time variability studies. In fact, almost everything we know about these innermost accretion comes from spectroscopic and photometric time variability studies. Decades of work, starting from Herman, Pearson, and like all those classic works which studied various emission line variability over time to understand what is happening. And over the last few decades, we have understood quite a lot. In fact, one of the things that we have understood is that the nature does not care about our desire to have a very simple, stable accretion system. In fact, it seems like most of these protoplanetary disks mostly accrete by episodic manner. And these episodic events are a nice hypothesis which actually connects and solves many open problems in the field of protoplanetary disks, like luminosity problem, the nodes that we see in outflows, the paths the stars take in the HR diagram before it reaches a pre-main sequence star, and so on and so forth, like the Kohn rules in our own solar system and all, all of which need some sort of like a heavy, fast flash heating of the disk to be formed. Observationally also, we have been seeing these phenomena, and these are called EXors and FUors sources. They are just those rare events caught on camera. And over the left here, you can see like a sample of the light curves of these sources, and you can see they come in all sizes and shapes. They are just all over the place. It's become really hard to actually classify them anymore as an FUors or EXors sources. So we had a long-term monitoring program to study these sources, because these are really great sources if you want to test your theories of accretion and what is happening and what is the outflows and so on and so forth. And they are also really important to understand, like, for example, from the exoplanet field point of view too, like, where is our snow line? How does these events move your snow line around? How the disk sublimation and all those stuffs. So our program was called MFIRST program, which is a multi-wavelength monitoring of FUors and EXors sources. And we have been observing these sources for now more than almost 15 years, using various telescopes, 2 meter to 1 meter telescopes in India, like 10 meter telescope SALT here, as well as other telescopes around the world. So in this talk, I'll just try to summarize some of the most interesting or exciting results we had so far from this program. One of that is on the question of what is actually causing these episodic state changes in the accretion events. So traditionally, the conventional way of understanding this has been borrowed from the cataclysmic variables, where you wait enough time, the disk gets accumulated, you reach a certain surface density, then you trigger some instability and drain up all the disk, and you then restart again the whole process. So one consequence of that model is that you expect to have a long period of quiescence before an outburst occur, and then again a long period of quiescence because you have to refill your disk. Which is mostly seems to be working for many of these sources, though we have been able to find a couple of sources, like for example V89N1 and V16 FUors and Orionis, which was in quiescent for a really long time, and then it came to an outburst phase, and these outbursts are like 4 magnitude or so. And then they remained in an outburst for a few years, and then it suddenly went back to quiescent phase. At that point, everyone thought, okay, this is done, like EXors, now it's going to be in a quiescent phase for a long time. But surprising everyone, it came back to outburst within a few years. So clearly, what happened was not the disk got drained and again got refilled, something else happened. This is not just one case, there are other sources also where this has happened. So in one of these V89N course, because we have this long-term monitoring program, we were lucky that we have spectroscopic observation too, spanning these transition phases. So the spots over here, I don't know, can you see my cursor?
No.
Okay. I guess I'll have to explain. Those tiny triangles that you see down there, those are where we had the spectroscopic observation, and you can see that we had spectroscopic observation just before it underwent back to the quiescent phase. And the plot over here is actually a sample from the H alpha lines. Like you could see that just before it went to outburst, sorry, I couldn't use my mouse to point out. The touchpad. Yeah, I am using the touchpad. I can see it changing here, but not, I don't see the mouse there. It's okay. But we're basically seeing like really strong outflows just before it went back to quiescent phase. So we don't know about the causation correlation, but it seems to indicate that, maybe something to do with the magnetic fields, as usually the answer is in many of these. And it's not just that. So that is quite interesting to see that you have something like that, but it's not just during that sudden change in the accretion that we actually see the variability. In this source, we are also able to see that wind variability is actually sometimes quite strong. For example, this is a Salt HR spectrum of this source, where the first plot is actually the jet shock region, the four-middle lines, which you can see the velocities goes up to something like minus 500 kilometer per second. And then in H alpha, like we were able to catch some of these high velocity P Cygni profile structures in high resolution from Salt. And you can see the velocities goes up to something like minus 750 kilometer per second. Remember, these are 1 to 2 solar mass stars, and the disk winds velocities you expect are somewhere around like 300 kilometer per second or so. So this is like a significantly strong wind. So back then we thought, okay, this might be some magnetically driven polar winds if the star is inclined. We are looking at pole on. So this could be a high velocity, unstable, and there were numerous works in literature, like including Romanova's group here, which shows like you can have such high velocity winds. And they are episodic, they are variable in nature too. Recently, Kospel's group actually did ALMA observations of this target and actually found the inclination angle is somewhere, at least the outer part of the disk, is somewhere around like 44 degrees. So now we are no longer sure actually how you would explain such high winds in these systems. And one thing is clear that these winds seems to be driven by the accretion event that is happening, or at least powered by that. Why do I say that? Because if we look at the source, on the plot over here, so you can estimate accretion from like the various different lines in the system of the spectrum shown over there. And what we see is that there was these P Cygni profiles which shows these winds, etc., when it is in the high accretion phase. And when it transitioned to the quiescent phase, all of that disappeared. Like for that period when it was in quiescent phase, the lines were very nice. There were no P Cygni profile structure at all. And then when it came back to outburst again, those winds reappeared. So which seems to indicate that at least on a long time scale, they do seems to be powered by the accretion process. Though I should mention that we also see variability in this even at short time scales. Like even during an outburst phase, there are like for few days when you will see like the line P Cygni profiles just completely disappear, and then again they come back. So it is definitely not like a very stable kind of a wind. There is definitely some instabilities there, whatever is driving it. There also another interesting result, we were able to see redshifted absorption in calcium triplet line. This is in one new EXor source we could completely characterize Gaia 20 AE. We could see this, that is actually an overplot of all the 3 calcium triplet lines which are believed to form at the magnetosphere. We could see redshifted absorption and sort of constraint, like, this could be a magnetospheric infall signature, so forth. The other source, the V899 source, actually turns out to be even more surprising as you keep observing this source. So the light curve over there from the assassin light curve, it shows that it has been in an outburst for some time, and in 2018 it suddenly increased its brightness again. So if you consider the photometry as a proxy for the continuum and as a measurement of the continuum, and then a proxy for the accretion energy released, you can see that there was like a sort of like an increase in 2018. Around that time, at that time we are commissioning our new high resolution spectrograph on the 10-meter Hobby-Eberle telescope. It's a near infrared spectrograph. We thought, hey, we have this instrument being commissioned. This is actually for radial velocity purposes, but no, instrument is not stable yet, but we don't care about radial velocity here. So we observed these sources at that point, and what we found was really interesting. So there are these lines like neutral carbon lines and SR2, which you see only in the low gravity environments. You don't see them in the protosphere of a protostar, but on like giants with low gravity and so on. So these are believed to form in the inner part of the accretion disk. What we see is that all of those lines, as accretion increased in 2018, all of those lines became really strong, and we see them in absorption. And then the accretion suddenly came back, like you can see the light curve went down, and these absorption signals, right, thank you, started dropping down, and they started decaying away. But soon after that, the accretion again went back, but the lines originating in the disk did not go back. It actually continued its decay, and after a few months, it actually started appearing in emission. Something that you would expect from a transition of a viscous heated inside hot disk to a radiation heated outside part disk. It is quite interesting to see that the accretion from if the photometry is tracing the infall accretion rate at the core of the magnetosphere, the disk thermal gradient profile is actually evolving slightly independently of that. And because this is a conference where there are a lot of experts on magnetospheric accretion, I also want to highlight another source that we found to be very surprising. This is again a FUors source, which is believed to be having a boundary layer accretion, and we see these low gravity lines having Keplerian rotation like you would expect from a disk. And in 2018 onwards, we have been slowly observing it, and what we started seeing is that a narrow component started appearing. So the disk temperature is somewhere around like 5,000 Kelvin or so, and these narrow lines correspond to something like a 3,000 Kelvin low gravity environment. And these lines have been like slowly growing and somehow like completely encapsulating the inner accretion part. So we are considering whether this is somehow indicative of some multi-layer structure, like sort of covering up like a curtain. At this point, you might ask, okay, we need more data. All right, so even the ASTRO 2020 decadal recommended long-term spectroscopic study to solve this problem of the protoplanetary disk system. There's only one problem, that is that it is too expensive to do spectroscopic follow-up. What we are working on now, I'll just quickly mention and then stop here, is a new instrument called TIFR MOONS. It's a novel kind of an instrument which works around something called A-omega conservation theorem in optics. The problem of doing multi-object spectroscopy with long wavelength is kind of hard. So we have a new architect which we believe will work, which can simultaneously take spectrum from about 350 nanometer to 2.5 microns optical near infrared, but up to 8 sources of any 8 sources in a 10 arc-minute field of view of the star. The goal is to conduct a world's largest spectroscopic survey of young stellar objects, and this will be a second generation instrument on the 3.6 meter DOT telescope. So we expect to have a rate of something like 100 YSOs per night, which covers a full wavelength range from optical to near infrared. With that, I will stop here for questions. Thank you.
Thank you very much, Joe.